Okay, so let's get started. How are you guys doing? Did you get a chance to do lab one? How many of you tried lab one? Okay, how many of you are planning to try lab one? Okay, so for people who have not tried lab one, we have put some additional resources for you. There is a help document which goes screen by screen on what you're going to be seeing, how you have to click, and how you kind of go from one step to another so that you can fire up your lab and do it right. Yesterday, we had some screen sharing issues, so what I've done is I've also created a video which actually walks you through the whole step by step, so that you can get to the Jupyter notebook, which we talked about. And I've given a brief summary of the various data elements we went through in Python. Okay. So just to recap what we did yesterday, so we kind of got a quick introduction to what data science is about. We got a very quick introduction to machine learning. Today we'll go into much more depth. And then we got introduced to the credit risk case study. And then we ran a lab on the sandbox to basically bring the data from an Excel or CSV file. And we looked at how do we understand the nature of the data by using pandas. And we used a couple of packages like Matplotlib and Seaborn to explore the data to understand the various bar graphs and pie charts and things like that. Okay, that's the the basics of how do you actually get data in and start exploring the data. Today, we have a couple of goals in mind. Again, all the slides and materials will be shared on Research Hub. So please keep watching the Research Hub. That's going to be your go-to portal for the next 3 days. All the labs and any specific instructions on how to go to the labs, the slides and the recording of this video will be available on the Research Hub. That will be one place to go and find out information like that. Okay. So we went to module 1 yesterday. I'm just going to try and orient this a little bit that way everyone can hear me. So lab 2, we're going to go through a quick introduction to machine learning and then apply these principles to the credit risk data set. Okay? And the goal of today is to give you a big picture on the kinds of models people talk about when you deal with machine learning in finance. Okay? And I'll cover 3 models, and one will be a traditional regression model. Another one would be a non-parametric model, it's a random forest model. It's what's called as an ensemble model. And the third one is the most popular model nowadays. When we talk about machine learning, we talk about neural networks. So I will give you a very brief introduction to neural networks and the kind of model you're going to be working with. Okay. So the goal of yesterday was to kind of bring in the data and understand the data. Today, we will build our first machine learning model. The goal of today is to build a machine learning model, not the best machine learning model. So we'll kind of get the constructs and we'll understand the principles of building a machine learning model. And tomorrow, we're going to go and figure out like how do you evaluate a model. Now, if there are multiple models, you have a choice of using which model you use, how you kind of bring in those models, and then what metrics you're going to be using to understand and apply those models. And the last day is talking about how you productionize all these models. Okay, so let's kind of start getting a review of some of the machine learning models out there. For the sake of what we are going to be doing, I'm not going to deal with all the machine learning models out there. We're just going to restrict ourselves to a family of models which we're going to be dealing with. And primarily, there are 2 types of models you'll be dealing with when you talk about machine learning. One is a supervised learning model, and another one is an unsupervised learning model. And in the supervised machine learning model case, we will typically, as we discussed yesterday, if you are predicting a numerical value, we call it a prediction. And if you are predicting a class, we call it a classification model. Okay? And in case we are trying to understand the nature of the data, we do not have labels associated with the data. We typically need to structure the problem. It could either be a clustering problem, where we are trying to build multiple classes based on the data we have at hand, or it could be something like a dimension reduction problem. Okay, so that's kind of the scope of the models we're going to be dealing with. So let's kind of formally set up the nature of the example in here. So in the supervised learning case, the observations we looked at, features we looked at with the data before. So those would be your set of variables. So given a set of variables, x1, x2, x3, the goal is to build a model f of x so that you can predict something which would be a y, right? Now, if y is numeric, we call it prediction. If y is categorical, we call it a classification problem. Okay? Now, when you start building a model, if you do not have labels, and there your observations would be things which you have recorded, and you need to put together a model. And the outcome would be something like, well, observation 1 is of class 1, observation 2 is of class 2, etc. If this is the structure of a model, then we call it a clustering model, and that's an example of an unsupervised learning model. Okay? So now that we have a generic structure of how these models work, so let's dig a little bit deeper. In the supervised modeling case, we have a couple of different kinds of models. One is what's called a parametric model. In a parametric model, the goal is you want to come up with a model which has a bunch of parameters. Right? And those would basically attribute to how these features are influencing the outcome of the model. Right? And if that's kind of the model you're building, those would be a parametric model. If you do not have a specification which has parameters, then you would call it a non-parametric model. And I'll give you a little more details in a minute. Okay, so let's kind of look at a very high level what a parametric model would look like. So basically, we assume some kind of a functional form, and the goal is to fit a bunch of coefficients. So the most common algorithm which typically used in the context of parametric models is a regression model, right? So if you look at on the left side, you have a bunch of observations. Your y-axis would be the one which you're trying to predict, and you have a bunch of x variables. If you just assume that you have one variable, let's assume that that's going to be your x variable, and the goal is to put together in the linear regression case a model which looks like y equals beta 0 plus beta 1 x1, right? So x1 are the observations you have already seen in the past, and y are the outcomes you have already seen in the past. And the goal is to basically fit the best possible model. You can use various techniques to do that. Ordinary least squares regression is one of them in the context of linear regression. And there, the goal is to come up with the best set of estimates, which is the estimates for beta 0 and beta 1, which is your intercept and your coefficient, right? So this would be an example of a traditional parametric model. Now, in the context of neural networks, what happens is, rather than just basically come up with an assumption that I'm going to be, asking it to be a linear model or a nonlinear model or a cubic model or some kind of polynomial model, you're going to be setting up a structure. You're going to be saying that these are going to be my inputs, these are my expected outputs, and then you have to provide the definitions for the various layers. You're going to be defining layers, and each one of these layers would have a node. And there the goal would be to say, well, each node would have these incoming weights and biases based on the prior layer. And my goal is to come up with the best set of weights and biases so that I can fit my input to my output. There you are more or less specifying the structure of the network and then letting the algorithm determine the weights and biases. Now, in the context of a linear regression equation, you would know that it's pretty simple to kind of compute these coefficients. You can use various techniques, an optimization technique, or it's just an inverse, just use linear algebra to compute inverse. We can use arbitrary least squares regression, come up with a line which kind of fits the best possible in this plane of or straight line, or if you're looking at multiple dimensions, the plane maybe. But in the context of neural networks, it's very difficult to structure, one analytical way of coming up with these estimates, right? At that point, you have to go with trial and error, and that's where a lot of technologies are used in the context of, estimates for these weights and biases. You start off with a set of random weights and biases, and then go through this iterative process, saying, okay, let's compute the outcomes and see how far away are we from the expected outputs, and then propagate back those errors. And there are various algorithms to kind of compute those estimates to get back, and then you propagate those errors, and then over these iterations, you'll come up with the best set of weights. And you can define the number of iterations you want to go through, and then establish stopping conditions saying, I will stop at this particular point in time, maybe the number of repetitions or the tolerance I would like to have. And based on that, the neural network will come up with a set of weights and biases based on the structure of the network we have, and that's going to be the structure of the algorithm. Notice that in the context of regression, you have to specify the equation before, saying it's going to be a linear equation or a polynomial equation or some kind of a structure, and then figure out the weights. In the context of a neural network, you have to define the structure of the network, and that's most of the times going to be the decision-making process on what kind of network I'm going to be choosing, what is the structure of the network. And you can take a very simple way of saying, well, let me start out with the simplest of equations, but the neural network gives you the ability to add more layers. And then you can define the number of nodes you want to have in each one of these layers. And nowadays, with deep neural networks, you have additional smart algorithms. You can say, I want to have a convolutional neural network or a recurrent neural network. You can define various ways in which you could structure your network, and that establishes the architecture which is going to be used for building out your machine learning algorithm. Okay? Since it's a quick introduction, I'm not going to go through the formal math or the specifics. Yes, please. So we basically have these layers called as hidden layers. You have an input layer and an output layer. You could have like multiple hidden layers. So you're going to be defining how many hidden layers you want, how many nodes are going to be there in each one of these hidden layers. And you can have multiple ones in that. And as you go more and more deep, you have like it's called a deep learning. Okay, so that's your basic parametric model. In the non-parametric case, you don't assume any kind of functional form. In the previous example, we were starting with an equation saying this is the kind of equation or this is the setup for an equation you're going to use it. In the non-parametric case, you don't start with an equation. You basically come up with, well, a random forest is the most popular algorithm for many of the use cases, but let's kind of go one step at a time. So in the past, there used to be what are called as decision trees. And CART algorithms, which are classification regression tree algorithms. So in these tree algorithms, you basically start with one node and you set up your decision criteria. If this value is less than this, then go here, else go here. And then you would kind of have these splits. And then you would establish a complete tree, and whenever you have an input point, you will start with one of these features, look at the value of the feature. Based on these features, you would go and come up with your decision criteria. And the whole way, the whole learning process would be to understand where those splits are going to be. This is based on many features, you're going to be figuring out where those splits are going to be. So that's going to give you one tree. And once you have a tree, you could use the tree for decision making. But random forest is basically what's called as an ensemble model. So instead of using a tree, you use a forest of trees, and that's why it's called as a random forest. So it's a forest of trees, and you use multiple trees, and each tree is going to come up with a decision, and you have some kind of a decision-making process. It could be a majority voting. So the first one may say X, the second one may say X2, the third one may say X3. If it's a numerical prediction case, I can come up with something like I'm going to take the median value, or I'm going to take the average value, or I'm going to take the minimum value, or maximum value, or some kind of a voting criteria. If it's a class, then if multiple ones says yes and a few of them say no, I can say I'm going to take a majority class and I'm going to use that as my decision criteria. So a random forest is typically what's called as a non-parametric model, where you don't have to start off with functional form. The algorithm determines based on the number of trees you specify how you are going to be setting up the criteria for decision. Okay. So just to kind of set the stage, in the case study we're going to be looking at these three algorithms: one regression algorithm, one neural network algorithm, and one random forest algorithm. So you have a choice of multiple machine learning algorithms, and when you do your testing, you'll figure out like some algorithms perform better compared to others. That could be the nature of the problem, the amount of data you have, the kind of structure you have. So it all depends on how you are going to be setting up your experiments, and then going about figuring out which algorithm is the best in your particular use case. Now it also comes to the context of the applicability. If you are trying to build out an algorithm, Can you hear me okay? You did something there? Yeah? Did you switch it off? Or?
No, I'm just setting the volume.
Pardon me?
Sort of echo, I think. Can you just try it again?
Hello? Can you hear me okay at the back?
Okay.
Can you hear me okay at the back?
Yeah.
You guys can hear me okay?
Yes.
Okay. Is the microphone working?
Yes, it is, sort of.
Sort of working? So we need to up the volume. Hello? Can you hear me okay? Hello? Does it work? Can I keep going? I want to make sure that the video, people who are listening to the streaming also can hear.
It needs to go a little higher, probably.
Okay. You don't do anything.
Yeah, if I go any higher.
Aditya. Okay. Can you hear me okay?
Faint.
Pardon me?
Not really.
Not really. Okay. Hello, can you hear me okay now?
No.
Aditya, let one of us control. If we both are controlling, it won't work. Just a second.
I'll leave it from there.
Okay, can you hear me okay now? Okay, can you hear me okay now?
Yeah, sure.
Okay, so let's continue. Sorry about that. There's feedback. How about now?
You're good.
Okay, perfect. Let's go. So we'll edit the video for the online viewers for a little bit. So that's kind of the structure of the algorithms you're working with. So we have three algorithms, two parametric algorithms and one non-parametric algorithm. So what I wanted to emphasize was the way you select your algorithms, you have to set up the criteria, right? For example, if you're building out a regression algorithm and you have a set of coefficients, you will know what the influence of each of these variables have on the outcome, right? So if it's a positive coefficient, you will know that the outcome is positively, the variable is positively influencing the outcome. If the coefficient is negative, you know that the variable is negatively influencing the outcome. So if you want interpretability in your models, you would want to make sure that you choose parametric models because you will know what these variables are and how they are influencing your outcomes. Especially in use cases like finance or in healthcare, you would want to figure out whether these variables are actually influencing your outcomes and if it makes sense to use these variables if there are, the values of the coefficients are really, really small. You can go about doing variable selection saying maybe I can just throw this variable. It's not worth collecting the data because it's having a very small influence on the outcome anyways, right? But if your goal is accuracy, or if your goal is to figure out like what's the best possible model, and I don't care the structure of the equation, it could be very complex. For example, in a neural network, if I look at the weights and biases, I don't really get to understand, what influence these variables are having in the outcome, right? Because you're going through a very complicated set of math. At that point, interpretability is lost, but at the cost of interpretability, you are going to be getting accuracy or some kind of a very complex equation, which is going to probably capture some of the nuances in the data you are currently working on, right? So you have to make more certain choices on if I use particular machine learning, what am I going to be sacrificing, and what am I going to get if I sacrifice this? And that's where the model selection goes in. We'll talk a lot more about it tomorrow. Now, in the context of multiple linear regression equations, so you kind of understand the structure. You're coming up with a set of estimates, beta 0, beta 1, beta p, and the goal is to minimize some kind of objective function, which is the sum of the square here, right? Okay, so let's move a little bit into classification. We're not going to be doing classification in the context of the next couple of days. But what we do in the context of classification is we add what's called as a transformation function. So you get a numerical function and then you transform it so that you can specify which class it would be. It could be class A or class B. Or it could be one of the multiple classes if you're doing a multi-class classification. And typically methods like logistic regression and neural networks are typically used for classification. There are other kinds of non-parametric models too. I talked about the basic decision tree a little bit earlier, but there's also what's called as a simple KNN model. If you're starting new and you don't want to figure out equations, you're just basically going to say that, well, I'm going to look at my neighbors based on some kind of a distance criteria. If my neighbor, if I have like two neighbors very close to me, for example, the green has two neighbors, which are the red triangles, and one neighbor, which is a blue square. So it's going to take a majority and say, I'm going to choose the two nearest neighbors, and I'm going to associate myself with the class of the red triangle. So the K stands for the number of nearest neighbors you're going to be looking at, and that could be a very simple criteria. So you are training your model and then figuring out like who am I close to, and if I have n number of neighbors, and then I'm going to associate myself with that neighbor. Okay, that's good. Yeah. Well, yeah, but in the k-means case, that's in the k-means algorithm, which we'll talk about in a little bit. You do not know what those classes are. In KNN, we know the classes already. So we already have labeled data. Yeah, so this is, we're already looking at labeled data. Okay, so in the unsupervised case, as I mentioned before, we have a bunch of observations. And the goal is to put these observations into a model so that you come up with the classes, right? And there are various methodologies you could use, and one is the most popular one is what's called as the k-means clustering model. And let's not go through the math. I'll kind of give you a little bit of basics as we go. But basically, it's minimizing the within cluster sum of the square distances. What it means is, if I have a cluster and I have a centroid, I want to make sure that the points in this cluster are closest to my centroid. Okay. So if I have, let's say, a cloud of data points, and I say I want 3 clusters, K stands for the number of clusters I'm going to be using. So the goal is to come up with 3 centroids, wherein each one of the points in my cloud can associate themselves with one of these points in this entire cloud. Okay? So you can define that K. It's a choice you'll have to make when you define your specification. You'll have to say I want 2 clusters, or 3 clusters, or 4 clusters. There are various criteria for choosing the number of clusters, and we'll talk more about it when we kind of do the case study. Okay, so let's. So this is just like a visualization of how the cluster is going to be looking at. One thing to note is you will have to think about like, well, what is anomaly detection or fraud detection kind of applications when you look at anomaly detection and versus unsupervised learning. So typically, when you're looking for anomalies, you want to detect the points which are not close to these centroids, or you want to look for points which are away from these centroids. And those would be the ones which you typically may not be able to associate with any of these centroids. The ones which are very close to the centroids are the ones which are normal that you've observed before, and model has already learned before. Okay, so one thing to note, I just want to talk about this and then move to the case study, is this notion of how do you define similarity, right? So when you have 2 observations, how do you define that these 2 observations are similar? So let's go to the simpler case where you have only numerical data. If you have numerical data, you can use a very simple measure like Euclidean distance. And this is basically the Cartesian distance between these 2 points. So you have x1, x2, and y2, y2, and you can define the Euclidean distance. And when I'm looking for similarity between points and the centroids, you just compute the pairwise distances. And then if I have 3 centroids, each point will compute the distance from that point to each of these centroids. And then the point will associate itself with a centroid which is the closest to that particular point. And then once you have all the points associating themselves with one of these centroids, then the centroid will say, well, why should I be so far when all my associated points are somewhere in here? The centroid will kind of move closer to these points, and now you have new locations of these centroids. And then you redo the whole algorithm to figure out like whether the points continue to be associated with specific centroids. So it's an iterative process. It's a computational and an iterative process. So it may take a little bit of time if you're working with really large data sets. There are some optimization algorithms to kind of figure out these distance computations using parallel computing. But for simplicity, you need to understand that you need to specify distances in order to compute similarity. So here you can expand the number of features from 2 to n, because the Euclidean distance will be, if you're considering x, y, z, which is points in three-dimensional space, then you're going to be computing the distance between these 2 points. Each one of them will have x, y, z coordinates, and you'll just be able to compute the distance with the same formulation. You'll have a z component here. You can just extend that to n number of dimensions, and you can compute the distance in n dimensional space. There are additional ways in which you can compute distance. One is called the Manhattan distance. If you're working with time series data, you can look at correlations. So there are various ways you can compute the distances. So you'll have to make a choice. Well, if I'm working with time series data, what is my similarity metric? If I'm using cross-sectional data sets with just numerical data, what's my metric? Now it starts becoming complex when you have both numerical and categorical data, because you don't want to just throw away all the categories, because if your data has like classes saying in class A, class B, class C, you won't be able to compute metrics. So you'll have to use some additional, more complex ways of computing distances. It's kind of beyond the scope of this particular talk. Okay, so the point here is, I think something happened with the slide. So basically you have multiple choices. So when you talk about machine learning algorithms, even with the simple setup we have, you have non-parametric and parametric models, then you have supervised or unsupervised learning algorithms, and then you have to decide whether you can be doing prediction, classification, or clustering. Right? So you will have to make those choices even before you get to using an algorithm, using your data and figuring out what your goal is. Okay, so let's kind of move to the lab. The data set we looked at yesterday was predominantly focused on exploring the data. So what we're going to do now is move to understanding the nature of the data and kind of build our model. So let me switch to the lab. So when you go into the research hub, we will have a link in here called as Lab 2, and this would be your machine learning lab. So if you click on this, you're going to see a help document, which looks like this. And this basically talks about the various things we're going to be doing in here, the associated Python packages which we're going to go and use in this particular case study. And then we'll, I kind of walk you through this and then walk you through the code. So we'll read the data. And this is basically what we did yesterday already. We will build out a clustering model, and we'll kind of look at some samples and work through the clustering model. We'll visualize using some techniques and understand the various clusters. And then we will compute some metrics. I didn't really get a chance to talk about the metrics earlier, but I'll kind of briefly talk about it today. And then we'll extend the discussion tomorrow. And then we will talk about what does it mean in order to build a machine learning model, what we need to do. And then we will save the model and go ahead and do the prediction. Now, when we talked about, just a second, let me just show you one more thing before we get to okay. So when you go into your lab, when you go into tasks, you should see a lab running. Everyone should have gotten an email that the lab has been started for them. So what we have done is all the code we are writing, we are putting it on GitHub. Okay, and then when we run a lab, it automatically pulls the latest code from GitHub. It takes all the requirements and packages all the Python environment things we need, Dockerizes the whole thing, goes to Amazon, fires up an instance, and makes the lab available for you. Okay, so the whole thing has been orchestrated for you, and currently this lab is running for an hour and a half. This lab we've kind of doing like a 2-hour lab, and then you will see a username and a password, and we will launch this lab. And once we have this, It's this is basically running on Amazon. And once we have this, we will have this work directory. You will see a data science crash course folder. We'll get in there. There's going to be a project. So we have the requirements.txt, the data we're going to be using, and the notebook we're going to be working with. So I'll go into the notebook. So yesterday we talked about the exploring data, and you can just fire that up if you want to just see what we did yesterday. But then today we are using the clustering and building models case studies, so we're going to be firing that one too. So we have two Jupyter notebooks. So a couple of people were asking me yesterday about why Jupyter notebooks and why not just build applications in Python locally. So one of the challenges is when you're building applications using IDE locally, the question is how do you share it with others, right? So you'll have to build out the Python files, the .py files, and then someone else should also have a similar programming environment so that they can understand and execute the code. With Jupyter, you can create a notebook, and it can structure the code in such a way that you can go sequentially from data ingestion to data pre-processing to model building to model evaluation, model deployment. So you can put the whole thing together in a logical workflow, and you can share that whole notebook, either the notebook through GitHub or a platform like what we are doing in here, where you can basically provide a lab, and then everyone can basically execute the same lab. So all the associated components which goes with building out the application, it's all structured in the application, so you don't have to worry about installation, configuration, trying out various things. So that enhances replicability and reproducibility. Especially if you're in an enterprise, traditionally many of the ways in which research was shared is through just graphics and through slides in conference rooms, right? So if you wanted to change the result, or if you wanted to change some of your assumptions, you had to go in and ask the quant or the data scientist to make those changes, run through the analysis, and come up with those assertions, and then start analyzing. But here you can get a live environment where you can get the whole code, and you can make those tweaks and changes, and everybody is seeing the same code. And you can replicate it, you can run through various configurations of your algorithms, and you can come up with the results and interactively understand what's actually being done and come up with better decisions. And it increases transparency, and also in the context of model governance, which is becoming a big issue with the enterprise. You have a structured way of enforcing modalities on how you're going to be building and sharing code within the enterprise, and also how you're going to be deploying it once all the code has been tested. Okay, so this was the exploration data set. We talked about using pandas, bringing in the data, and kind of understanding the data. We did observe yesterday that when we explored the data, we had a bunch of numerical and categorical features. So today, what we're going to do is extend the lab. So we're kind of bringing in the data. So for people who have never used Jupyter before, I have to make one more clarification. So you can run this code live. There is this notion of cell in here. You can go into cell and you can run individual cells. Each one of them is a cell. So you can run individual cells, or you can just say run all, and the entire code runs. You can run this as you kind of go through it. This is all live code. If you need to make any changes, you can always make those changes. The lab itself, you can replicate it. So you have these $50 worth of credit. So if you want to go home and you want to start up a lab, I put together a video in the Research Hub. So if you go in and look at this lab instructions video, so it talks about how you basically set up a lab. And we will provide a link, what is called as a Q link in here. So this basic link will connect you to Sandbox, and you can fire up a lab just by clicking this button and authenticating yourself. So it will track how many hours you're going to be using. So the one additional thing I wanted to also mention was if you want to increase the duration of the lab, so you can just click on this button and you can extend the lab and you can increase the duration of the lab. Okay, so let's get into the clustering case. So yesterday we talked about leveraging the data through NumPy and Pandas, and we talked about some visualization. So today we're going to talk about some of these machine learning algorithms. In Python, there's a library called as scikit-learn or sklearn, and that basically has a bunch of different algorithms. And we're going to be using some of those algorithms to basically implement the three algorithms we talked about in the slides earlier. Okay. So in the context of data, we have the Lending Club data which we are bringing in, and so let me kind of prepare some of these categorical variables. We're doing what's called as, in the context of what we're doing, we are mapping these categories to numbers that can play around with them. You can also use another technique called as one-hot encoding. So it's basically like binarizing the categories. So instead of just saying A and B, you can say 0, 0, 1, 0, 0, 0, 1 kind of thing. You can encode those variables and create any variables and use those for classes. Okay, so once we have the data, our goal is to compute interest rates. We'll first kind of understand the data and try to cluster it and then compute the interest rate. So you can see if you look at the minimum rate, the maximum rate. So you can see that the minimum rate which was offered on Lending Club was 5.42%, and the maximum rate was 24%. So let's kind of start using clustering. So I talked about the k-means clustering. So the k-means clustering uses, it kind of creates based on the number of clusters you have chosen. It minimizes the different clusters of the square distances, right? So here, in order to figure out which k is the best k for the data set we have, we are using a methodology called as the elbow curve. And the goal is just think about a cloud of points. It all belongs, by default, if they are not having a cluster before, it all belongs to just one cluster, right? So if I think about a centroid, just putting a point which is the minimum point for all the associated points in this cloud, then each one of them will be having a distance, and that's like, if you compute the distance, that's going to be like the maximum distance, right? And then if I have two clusters, then the distances, the sum of the square distances will actually go down, right? So as you increase the number of clusters, the sum of the square distances between the cluster and the points actually go down, right? So think of if you have the number of clusters equal to the number of the data points you have, then the sum of the square distances will be 0, right? Each point will be its own cluster. Then the distance will be 0, and you compute all the sum of square distances, it will still be 0, right? So you might have, on one extreme, you could have only one cluster, which is what you already have. On the other extreme, you could have the number of clusters equal to the number of data points you currently have, right? So you want to figure out like what's the happy medium. You want to choose the number of clusters which realistically gives you the bucketing you're looking for and has majority points in those clusters that actually makes sense. So that's what we're trying to do using this elbow chart. And we are going to be ranging from 1 to 20 clusters. And we are going to be calling this k-means algorithm. Notice that in Python, you won't have to implement these algorithms. These algorithms are already implemented for you. You just need to understand the algorithm, the parameters which you should be passing to these algorithms, and specifying those parameters appropriately when you call those functions. Yeah. And there's enough help. You just do Google and you'll find documentation for those algorithms so you can work with them. So here, something happened again. Is it good?
We lost you.
We lost it?
We lost you.
Okay. I think we tried that a couple of minutes ago.
Yeah.
Okay.
Okay.
Is it good now?
Yeah, I'm putting it back up the volume.
Okay, it's going to get better?
Yep.
Okay, good. Okay, so here we have the k-means model for all the data points, and we are putting these k-means, and we are computing this metric called as distortion. Okay, so it's basically the cost function. What the goal is to minimize this distortion, and it's basically the sum of the square distances between each observation and closest centroid. So when you review the case, you have more details about what it is, and we'll also post some information on get some additional information on the algorithm itself. So when you plot it out, you can see that when the k is very low, the distortion is pretty high, and you can see that the slope of these lines, when you increase the number of clusters, kind of start going down. Okay, and you will think about the happy medium, like if I have like only 2 clusters, I will have distortion to be around 23 or 24,000. But if I have a cluster size of 5, then the distortion goes down to 15,000. So then you can decide like, well, if I wanted to get that distortion down to around 10,000, then you need to increase your number of clusters. But if you have like 10 clusters, it actually makes sense. So you can choose based on the use case, like how many clusters you want to go with. Okay, so let's say we go with like 5 clusters, and then we run through this algorithm with these samples in here. You can notice that in the first cluster, 5,210 points kind of associated themselves with the first cluster, 1,000 points on 2 clusters, 108 for the third cluster. There's only 1 point which associated itself with the fourth cluster, and close to 3,626 points associated with the fifth cluster. Okay. So, and then you can like play around with like these clusters, depending on, you're just at this point basically trying to figure out there are 10,000 records I've observed. Can I bucket them into individual clusters? So what are those use cases? If I did not know the nature of the data and the dependencies of these variables, one thought is to say, let me do the clustering and then start building models associated with each of these clusters. Okay, so that's one way of looking at it. Another way of looking at it would be to say, once I have these clusters defined, then I can look at the ones which are most influential, and then start, thinking about algorithms for the most influential ones. Once I kind of start evaluating them. So you may have to go through a process where you build out these clusters, then do what you did yesterday, which is EDA. For that particular cluster, can I evaluate the data? Does it make sense for building out the model? What is my target audience? What kind of models am I trying to build? And then associate with visualization, then come up with questions there. Yes, please.
When you have more than one centroid, how do you locate the centroids?
How do you locate centroids?
Stepwise, or how do you?
Oh, so here what we are doing is we are basically going from 1 centroid to 20 centroids.
Right.
So we're basically iterating it. So it's basically saying start with 1 centroid, then 2, 3, 4. So those centroids, you can specify the start points, or it would be randomized. But the point is these centroids will move in space based on every iteration. It's an iterative technique. So the first time it will kind of randomly select 2 points. Let's say if you start with 2 centroids, compute the within cluster sum of the square distances for all these points. These clusters will move closer to those point space, and then you kind of start iterating, and then you figure out like the best centroids for the points you have at hand. And then you kind of figure out like the best 3 centroids, best 4 centroids, best 5 centroids, and kind of iterate. Yeah. Got a question or point, sir? Yeah, and that's what's K. So K basically means how many clusters do you want to have. You can have K equals 1, 2, 3, 4, and whatever number of things. You could have multiple solutions. If you enumerate enough, you may gravitate towards 1 or 2 solutions. Yes, please.
But for any given K, as you optimize the next one, don't you de-optimize those that preceded it?
I'm sorry, could you repeat the question again?
For any given K, any given number of K, as you step through the centroids and you optimize, you get your least squares on the one you're currently iterating. Don't you de-optimize all the others that you've already solved for?
Yeah, we may want to take the discussion offline, but the point here being, you're going to set up a set of criteria saying that give me the best 2 centroids for the data set you have at hand. And it's going to randomly start, and then based on the pairwise computation of the distances, it will figure out which are the 2 best locations of these centroids. It's kind of an optimization process. You could randomly start and it will kind of gravitate towards those 2 points if there's one solution, but typically based on the stopping condition, you could end up with different locations of those 2 centroids.
Do you get there by simulating rather than by some kind of linear optimization?
Exactly, yeah.
Okay.
You're not technically optimizing. This is not an optimization problem. It's actually computationally, it's an iteration problem. You're basically saying for each one of these, compute all these pairwise distances and kind of run through it.
Thank you.
Okay, so here, once we do that, there's also a technique called as T-SNE, which is a way of visualizing high-dimensional spaces in 2 or 3-dimensional spaces. So that's one way of looking at the nature of the clusters you have. I'm not going to spend too much time on this because we want to move to the prediction case. But when you plot this, you are now, think of it as like a PCA, wherein you have, let's say, 15 or 16 different dimensions. You want to reduce it to 3 dimensions, and you're plotting those 3 dimensions. So when you see that this would be like the nature of the clusters, So you could see that these are all in one cluster. You have this one point, we have in this cluster. These are all in another cluster. These are all in one cluster. So you can kind of visualize this n-dimensional space in 2 or 3 dimensions to get an idea of how these clusters are structured. Okay, so that's a little bit about unsupervised learning. So the goal here is to figure out, well, I have a lot of data. I don't know anything about it. There are a lot of numerical and categorical features. I want to be able to segment this into buckets so that I can individually assess these buckets. And clustering is a way of potentially doing those segmentations. Now let's kind of look at the next thing, which is so in this particular case, we are doing some additional analysis to figure out the nature of each one of these clusters. So you can kind of plot it out, saying, well, in the first cluster you have the loan amount, this is the average loan amount, and this is the mode of the loan amount. The annual income, the mode is 60,000, and the mean average is around 42,000. For the next cluster, you can see that the average loan actually went up for 15,000, and the annual income was also higher for the second cluster. In the third cluster, the loan amount was close to 20,000, the annual income was close to 120,000. So depending on the nature of the average data point, you can kind of build out these clusters, and you can try and understand whether this is the kind of cluster I need to work with for the model I'm building. Okay, so let's move on to the machine learning example for supervised learning. So here, one thing we're doing is do some data preparation. The scale of each one of these features are actually different. So what we're trying to do is start with the normalization. So we're going to be normalizing the data so that the scale should not affect a lot. Some algorithms require normalization, some don't. So once we have that, we have to do something interesting in machine learning. In traditional statistics, if I'm trying to understand the nature of the data, which I've seen historically, I can throw the entire data set and build a regression algorithm, and then figure out, look at the ANOVA tables, look at the coefficients, and start making calls. Right? Here we are trying to build a machine learning solution. And the goal here is to build a generic solution which could be applicable for prediction in the future. So the primary goal is to figure out the predictability of the algorithm which we are trying to build up. So the way we do it is take my entire data set, and then slice this data set. So we kind of split this data set into an 80-20, let's say. And you say 80% of the data is what I have. So let me model, build out a model for 80% of the data, and take this model I have built with the 80% of the data, and test it for this other 20% of the data which the model has never seen before. And then build out the predictions, and then figure out how good my predictions were compared to that of what I had already seen as historical observations. And then compute my error metrics. So the goal here is to say, rather than just take my entire data set and build out a model, figure out a way in which I keep aside some part of the data I've never seen before, and then build my training data set, then build the model with my training data set, and then test it. So if you go to Kaggle or any other platform for machine learning, you typically see these training and testing data sets. And then you'll have to figure out which is the best model I can build with my training data, and then test it out. Okay? So that's what we're doing in here. So we are basically splitting the data, taking my entire data set and taking 80% of my data as training data, and then 20% of my data as testing or validation data. Okay? So tomorrow we'll talk a little more about cross-validation and things like that. And then we'll kind of expand upon it. Yes, please. It depends on the data you have. There's no real rule. If you have a lot of data, you can even start with 90-10. But if you have very little data, if you have very little data, then you'll have to figure out, if I want to capture the nuances of the data, I may have to start with a really large number, and then probably augment it with cross-validation and the techniques. If you have really large amounts of data and the variety is kind of all over the place, then you can randomly split it into 60-40 or 70-30, whatever. Okay, so we got the data set in here, and we are creating the training and testing data sets. So here we are defining a couple of metrics which we didn't talk about yesterday. I'll briefly talk about it. So this is kind of the decision criteria. You need to figure out what am I trying to minimize? right? So I want to build out something which I'm trying to minimize, and here we'll talk a lot more tomorrow, but we are primarily trying to minimize either the root mean square error, or the mean absolute error, or the mean absolute percentage error. Which basically means that if this is what I've observed, and this is what I'm predicting, and how good is my prediction compared to that of what I observed, what's the percentage error I'm going to be computing, right? In the context of root mean squared error, you are basically taking each one of these values, and then on an average, how good is my error metric, right? And then here in the mean absolute error, you're basically taking an absolute number for the error, and then just taking an average of all the errors. Okay? If you don't take an average, or rather, if you don't take an absolute value here, if you just add up all the errors, right? Okay, so this is what we are trying to do in here. So let me get back to the case in here. So in order to compute those metrics, we are basically defining some simple helper functions. There are also methodologies in scikit-learn. You could just use that if you don't want to write your own functions. And then we are building some functions to just plot out the data. So now let's, I don't know why, I think the images didn't show up. So we need to look at it. There are 3 images. We need to just check why this not, they may not be like there may be an absolute reference to the images. We need to check that. Okay, so let's look at the regression algorithm. So here we are basically saying build a model with the training data and with the Y training. And then here you could, once the model has been fit, this has actually all the parameters of the model. And then you could use a predict function and pass in the test data and come up with your predictions. And then you can plot out your predictions versus the actual observations. Okay? So as you can see in this graph, the orange represents the true values and the blue represents the predicted values. So in some cases, for the testing data we had in here, we just took 50 samples for plotting. You can see some of them are very close, some of them are further apart. Okay? And then you could take the entire training data set and you can plot it out. This doesn't make very much sense here, so you can start with some summary metrics. So the regression model basically said the mean absolute percentage error was 19%. So you were off by 19% on an average for the results you're computing with the simple linear regression model with that. Okay. So then we look at this non-parametric random forest model we built earlier. So again, here you don't have to specify very much. You specify the random forest, how deep you want the model to be. Here we just said the depth should be a maximum of 5. You can set up your random state where you want to start with. You're just setting it as 0. And then you fit the model, and then you specify a bunch of other parameters, and then you kind of get the model and plot out the predictions in here associated with the random forest model. And this is what you see. When you look at the summary measures, the error went down from 19% to 6%. And so random forest actually performed much better compared to that of your linear regression model. Okay? Yes, please. Yeah. Well, we're not practicing maximum. We are predicting the interest rate, not the maximum. Yes. Right. Yeah. So whatever comes up as when you look at the entire tree, you basically end up with the average in here. So if you have a bucket of numbers, each one of them having different interest rates, because you have chopped it off at depth of 5. So based on the tree, it basically takes the average at that particular leaf of the tree. So if you have numbers, you just don't, you don't have a class. You basically have a bunch of numbers. You take an average. Yeah. Okay. So the last one is your neural network. And in neural network, what we are doing is we are specifying the layers and the sizes of each of these layers. So here we have to make a choice of a bunch of different things, and we won't be able to go in depth tomorrow. I'll try to cover a little bit here. But the point here is you need to specify how fast do you want to learn, because you're going to be setting up your delta saying, in this first iteration, I'm going to have a learning rate of so much. Do I want to keep the learning rate to be the same? How many times I'm going to iterate through the whole process, and that's something you need to specify. And also you need to specify what's the stopping condition, what's the tolerance you want to go. If you learn in the first iteration and they go into the second iteration, if you aren't learning much, then you may want to stop, right? So that basically, are some of the parameters you had to specify. You had to specify your optimization algorithm, and then once you fit the model, it goes through each one of these iterations, and you can see that the loss function actually starts decreasing. So here we went through a maximum of 300 iterations, and it went to, this is like the least it went to. And then when you start plotting it, you can see that this is the true and this is the predicted value. The oranges are the true and the blue are the predicted value. We did not really do a lot of engineering in the context of the network itself. But with the simple network, the error rate actually went down to 6.56%. When we looked at the random forest, it was 6.07, and the neural network with this particular architecture is 6.56%. So when we compare the model parameters, when you look at the interest rate, for the testing data, for the linear regression, we had a MAPE, or the mean absolute percentage error, of 19%. For the random forest, it was 6%, and neural network, it was 6.56%. Overall, if you start looking at various numbers, linear regression gave like the worst results, and neural network was better in some cases. Actually, the random forest was the best in all the three cases. Yeah, so in all the three cases, random forest was better, and neural network was very close. So what we're going to do from now on is we need to optimize this model. We just built our first model with a bunch of parameters. So tomorrow we're going to look at some of these metrics a little closer and figure out a way in which we can try and optimize these numbers. And then we'll also look at criteria you could use for your training and testing so that you can compare some aspects of whether you're overfitting or underfitting the model. Some of the things you need to figure out when you are trying to build out imbalanced data sets. If you have data of one class to be largely there compared to that of another class, how do you actually work with those kinds of data sets? And then we'll also figure out how do you compare training and testing data, and then how do you choose a model if you wanted to deploy it for production. Okay? And then there is a methodology which is called pickle, which is basically taking your entire model and then dumping it onto your hard disk. So the next time you want to run this model, you can print this model and then use this model for prediction in other cases. So we'll talk a little bit about it more. Okay, so it's 4 o'clock. We have to stop the recording now. If there are any questions, I can take them, and we'll be hanging around afterwards if there are any more questions. Any questions before we end the session? Yes, please. Mm-hmm. Yeah, so TensorFlow is prominently, it's an open source platform. It's currently supported by Google. It's primarily used for building deep learning neural networks. And you can structure a basic neural network, but you can also specify various iterations or various varieties of neural networks, like convolutional networks, encoder-decoder networks, or RNNs, or GANs. So the different versions of neural networks which are available, you can potentially structure them in the context of TensorFlow. So it gives you a very flexible ability to build deep neural networks. So that's how TensorFlow fits in the picture. And it has a Python interface, so you can definitely integrate that in Python and build applications using TensorFlow. Okay, so if there are no more questions, we'll adjourn for the day. Oh, there's one more question? Yes, please. Oh, okay. So here, okay, so let me just kind of look at this. So here, so we'll take the feedback, we'll augment this probably. So here what we did was when we viewed this data, so the predictions were what we were predicting in here, right? So we basically used this predict function to take the text data and then we predicted it, right? So these were the interest rates. So we had an interest rate. This is like the normalized value because we normalized all the values from 0 to 1. So the maximum interest rate would get a 1. The minimum interest rate would get a 0. So we have normalized this axis. Okay? So amongst the test data we looked at, so we had a sample of 50, right? So each one of them is a test point. Exactly. Yeah. So each one of them. So this was, one of these data points. The predicted value was around 4.5 in the index of 0 to 1, but the actual was close to 0.46 or 47 or something like that. So the closer these are, it means your prediction algorithm is good. This was randomly chosen. That's why you see the points all over the place. But there are other ways. Tomorrow we'll actually show one more graph where you can actually plot your y versus y hat, and you would expect the points to be on the diagonal if the predictions were good. If it's all over the place, then the predictions were not good. Well, we are just, in this particular case, we are using a multiple linear regression because we are using all the 17 different features. Yeah, exactly. Yeah. Okay, so let's, we'll be hanging around if there are any more questions. So people who are listening online, we'll be posting more, some more information for the labs and other stuff. But if there are any questions, feel free to email us and we'll go from there. Thank you so much and see you tomorrow. Thank you.